Thank you very much, Eric, for the introduction. 40 years, my goodness, it's a long time. So, yeah, that's right. You were a graduate student at Princeton when we got to know each other in 1982 in the fall, right?
41.
Yeah, that's right. So I also would like to thank Patricia and Anna for this kind invitation. And I'm really sorry that I sort of couldn't manage to get there of various issues. So so this is a course. And I decided not to produce slides. I mean, I have them, but things go too fast with slides. And I thought I might well use my newly acquired tool, GoodNotes, to write things down. And I hope you can read my handwriting. So let me start with a motivation of why we want to look at Spinor inequalities and zero modes for the Dirac equation. And then there are numerous motivations, and one of them is the hydrogen atom. And so let me talk about the hydrogenic atom. I say hydrogenic because I want to keep the charge number not fixed, arbitrary. Hydrogenic atom. So of course we all know what this is, right? I mean, since I don't know our undergraduate days, this is the Hamiltonian, and X here is in R3. And it acts on wave functions psi. I mean, this is also to establish notation which take values in C in general. And the ground state energy, E of Z is, of course, we all know that, the infimum over all these energies, minus Z psi squared over X. And of course, you have to have a normalization condition which is consistent with the probabilities interpretation, right? And we all know that, I mean, this is this famous example, right? Namely, that the uncertainty principle, if you want to make the potential energy very large negative, you have sort of to squeeze this function into the nucleus. But then, of course, the kinetic energy starts exploding, and that balances each other out. And you get this incredible result that this minimization problem gives you essentially the right order of magnitude of the radius of the hydrogen atom. In fact, EZ everything can be nicely computed, which you remember, of course. And the function psi, which minimizes this, is a constant times e to the minus z x divided by 2. That's what it is, right? So the uncertainty principle is here the key. Now, what happens when you turn on a magnetic field? Magnetic field. Well, what happens? Well, so remember a magnetic field. This is a map, if you like, from R3 to R3, mathematically speaking. But the crucial point is, of course, that its divergent vanishes. And then what this entails is that you can write the B as the curl of what is called the vector potential. And for some strange, odd reason, it's the vector potential which plays the big role in quantum mechanics. And the magnetic field only enters in a sort of an indirect fashion into this business. So hydrogen atom in a magnetic field, what is the energy? Let me say it this way. Oh my, I don't understand. This thing flips around sort of at will. E, D. The D stands for diamagnetism. We will talk about this. What is it? It's the infimum, of course, of this gadget here. That's how the magnetic field enters the energy. It's very strange. And I mean, it's something which one just has to accept. That's what this is. Okay? Now you notice, by the way, that the vector potential is not uniquely given, right? You can add a gradient to it, and it will not change the magnetic field. And since the magnetic field is really the physical quantity, you hope that this should not affect, in other words, when you choose a different gradient for the A, it should not affect the energy. And this is given by what is known as the gauge invariance. And what it says is, if you changed the psi into e to the I phi, and this can be dependent on x, of course, right? And the A into A minus grad phi, you do not change the energy. And you see it's pretty clear, right? Because the A gets changed by this gradient. That gradient gets picked up again from this term, and they really cancel out. So this is what is called gauge invariance. And you see also that the potential energy doesn't change, and of course the normalization doesn't change either. So these are somehow, now here's an interesting point. When you look, so clearly this energy which you have here will depend on the magnetic field, right? And I also mentioned this letter D, which calls diamagnetic, and this has to do with the following. This complicated function is always bounded below by E of Z. And this is called diamagnetism. And this has to do with Kato's diamagnetic inequality. Now, why do we, by the way, what is diamagnetism? Diamagnetic inequality. It's the following. There are certain materials which, when you try to put them in a magnet, they want to get out of the magnetic field. These kind of materials are called diamagnetic. And there are other materials which are attracted to magnetic fields. And these are called the paramagnetic materials. And this is, I mention these things because this is going to be important eventually. And so what does this diamagnetic inequality say? It says the following, that if you take any function psi in H1 of Rn, so this is a complex valued function, Rd, let's call it Rd, then pointwise almost everywhere, minus I grad minus A psi is greater to equals the gradient of the modulus of psi, and then you take the magnitude. That's the diamagnetic inequality. Now, when you accept this, of course, you see right away that when you replace this term with this inequality, you are back with your good old friend, namely the hydrogenic atom. And therefore, by minimizing that problem, you see right away how this inequality pops out. So this is extremely pleasant, right? Because it makes analysis and inequalities and lower bounds much, much easier. By the way, this inequality also key for stability of matter with magnetic fields, okay? So in order to, since this is a course, let me also prove this. Why? Because this sets in some sense the stage for certain things which you will use frequently. So this has to do with Sobolev functions. So imagine you have a bunch of Sobolev functions. U is a vector. And I will use this now to prove the diamagnetic inequality. And so you have n functions, in, and each function is in W1P log. And this can be of some domain. It can be all of Rd. It doesn't really matter. Okay. So let me not specify that. Remember, W1P log is all those functions whose weak derivative exists and is in LP. So, and then what you then form is you take a function G from Rn or Cn, I should say. Well, it can be Rn, doesn't matter. To C, which you assume to be differentiable, continuous derivative, and bounded derivatives. So the function should be bounded, including its derivatives. No, only the derivatives, sorry. Good. And then you form K composed with U. And then it turns out that this function is again in W1P log.
Michael, is KG?
Sorry?
Is K?
Sorry. Yeah, K equals G composed with U. Thank you. So K is equals G composed with, thank you. That's what I'm saying. Okay. This is again in W1P log. And you can differentiate your K in the weak sense. I'm writing it this way in standard ways, right? And then duk, dxi. Moreover, when the G has the property that it vanishes at 0, then when the U's are in W1P of Rn or Rd, then K is also in W1P of Rd. I mentioned this, so the proof of these things is quite easy. It's a standard which you find, say, in Gilbert, Trudinger, and other books. And the nice thing about this also allows you, for example, to differentiate the magnitudes. In other words, when, for example, a function psi is in H1, then its absolute value is also in H1. Okay? So this is something which you will use frequently and is quite easy. And the point, of course, is these are weak derivatives, not the usual ones. So let's prove the diamagnetic inequality.
Where does G of 0 equals 0 come in?
Because you see, it could be when the G of 0 is not 0, then the function K would not decay at infinity, and then it wouldn't be integrable. Right? Mm-hmm. I mean, you stick in the function U, which goes to 0 at infinity.
Right. So we need the derivatives to be in LP, but yeah. It was locally.
No. Yeah, so for at the beginning it was local, but here when I have the derivatives bounded and the function vanishes at infinity, at 0, so then the composition.
Okay, great. So W1P not local, right?
Yeah, well, W1P, not just local, right? Exactly. So this is a sort of a standard thing which you find in many textbooks on PDEs. Yeah, and I will use this frequently. Also, the absolute value. So let's prove this the diamagnetic inequality. How this is done? You notice that. So you take your psi, say in H1 of Rd, and you write the psi in the form real part and imaginary part. I. Okay, and then you differentiate the absolute value. And this is a standard formula, which is nothing but the real part of psi complex conjugate divided by its absolute value times dj psi. And this is when psi is not equals to 0, and otherwise it's 0 when psi vanishes. Okay? This is again a formula, and notice, by the way, all the derivatives here are weak derivatives. So now you see right away that the gradient of the absolute value of psi, what is it? Well, you see, you can, sorry, I should have said this before. When I look at dj psi, I can also add for free, since I have the real part here, dj plus I a j component psi. Do you agree? This is when psi is not equals to 0, 0, psi equals to 0. So this is for free. And now, of course, it's extremely elementary by just, absolute values and remembering that the absolute value of the real part is less than the magnitude. you immediately find that gradient psi is less or equals gradient plus IA psi, pointwise almost everywhere, right? So this is this famous Quantum inequality, and we're going to encounter this in various forms afterwards, okay? Good. By the way, when there's any, please, Eric, keep complaining, right? This is very good. Appreciate that. When you find mistakes. So now the next thing is, this is not the full story, right? As soon as you turn on magnetic fields, even for the hydrogen atom, spin is going to be important. So what is so electrons carry spin. So what is that? So I cannot describe any more an electron, but once you take into account the description of an electron is really by two functions. And this is what is called the spinor. Psi j, there are, of course, values in C. And we assume, and we put on the usual inner product. When you have two spinors, phi and psi, what is that? That's nothing but phi 1 complex conjugate psi 1 plus phi 2 complex conjugate psi 2. And we note this with this bracket. And of course, a spinor should also be normalized in the sense that when it takes its inner product with itself, and they integrate it, that should be equals to 1. So in some sense, I have two kinds of electrons. The electrons with the spin up, which have only the upper components, the electrons with the spin down, which have the lower components, and the probabilities for having an electron in the upper component and the lower component is, of course, in total 1. Okay? So, and along with this spin, in the dynamics shows up the Pauli matrices. So Pauli matrices, this is another one. And how do they look? So there are three matrices. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I plus I here, 0. And sigma 3 is equals 1 minus 1, 0. So it's diagonal. Very often I will call sigma simply the vector sigma 1, sigma 2, sigma 3. Okay? There are a number of simple computations. When you, for example, take a spinor psi, and you compute psi sigma 1, then you get the real part of psi 1 complex conjugate psi 2. If you take psi sigma 2 psi, that's the imaginary part of psi 1 complex psi 2. And finally, psi sigma 3 psi, you get psi 1 squared minus psi 2 squared. Right? I mean, I just wrote it down. And so what you now see is, and this is very easy to see, it's the following, namely, if you take psi sigma psi, this whole vector, this is now a whole vector, and you take the magnitude of this vector, and this is going to be important. This turns out to be what? Well, you square this, you add this up, you square this, and what you notice is, well, maybe I screwed up, this should be a 2. What you notice is that from here, from this side, you get a minus 2, from this guy, you get a plus 4 in the cross terms, and that goes up. That gives you in total a full square. So that's psi 1 squared plus psi 2 squared. Okay? So this is, so in other words, this is psi psi. So this relation is also kind of important. By the way, this has another nice feature. If you take sigma, and you take this vector psi, sigma psi, and you divide by its length, that's a matrix, right? A 2 by 2 matrix, it's a Hermitian matrix. And now it turns out that this matrix has the nice property that psi itself is an eigenvector with eigenvalue 1. This matrix here, by the way, has eigenvalues +1 and -1 because the length of this vector here is 1. Okay? So these are a little bit, hopefully you get a little bit used to this kind of jiggling around with Pauli matrices, but these identities will be important for what's coming up, okay? All right, so now let's go on and say, what is an electron now? Hydrogen atom in a magnetic field, now with spin. So we get now an energy, which is now the inf, and well, this is our good old friend, minus, and now comes an additional term. So this describes, so these two things together, right, describe in some sense the kinetic energy of the electron. And oddly enough, you also introduce here an interaction. You have to sort of think as the electron as almost like a needle, right, a magnetic needle, which interacts with the magnetic field. You notice these terms you would not see at all when the magnetic field is 0. But since it's not 0, you definitely see it. And then, of course, you have minus z, the integral psi squared divided by x. And you minimize this, of course, over all spinors now, which are normalized. Okay? Good. So now this functional opens up a whole kind of worms. The thing is that in general, this energy now, which still, it depends now also on the magnetic field, is less than E of Z. So in other words, this second term here, you see this first term pushes the energy up, right? This second term has the tendency to push the energy down, and this term wins. In fact, you can easily cook up magnetic fields. When you let them get the field strength very large, you can make the E of P can be made negative, as negative as one pleases. Also, you notice this Hamiltonian is still gauge invariant, right? Because when you dress up, when you take each of the spinor components and you multiply them by a phase, I mean, by the same phase, I should say, then things don't change, right? I mean, when you multiply it by different phase, then things change, of course. That's not gauge invariance. But when you multiply the whole spinor by a phase, this doesn't change, and this doesn't change either. Psi sigma psi is gauge invariant. The phase drops out. Okay. So, and now, this is of course a problem, right? And this brought us many years ago to the following idea. This is in some sense the main motivation about this whole problem. Namely, you see, if you, the idea is a little bit that you think in terms of fluctuating fields around you, right? So you have large magnetic fields, they also always come. And wouldn't it be terrible if by some fluctuation you can make the field extremely negative? But of course, such magnetic fields, which you get, you have to produce them somehow, right? And so the idea would have been to look at the following functional, which depends now on Z. You take the infimum over all magnetic fields, you take this paramagnetic energy, right? In other words, including spin. And what you add to it is the field energy, because that's in some sense what you have to pay to the power company. And I apologize, but in my units, it's atomic units, this constant depends on what is called the fine structure constant, which is 1/137, about. So you notice this is, in atomic units, a very large number. Okay? So now you take the infimum over that gadget over all possible magnetic fields, and you come up with the question, is it really true that this infimum is greater than minus infinity? All right? So mathematically speaking, this boils down to the following, to consider the functional E of psi and A, or psi and B, I could also say. Ah, yeah, before I forget, here's a neat identity. When you look at minus I gradient minus A squared minus sigma dot B, that you can always write as sigma dot minus IA minus A squared, okay? And that's an interesting computation which I recommend everybody to do. I think the first time I learned it was from the Feynman lectures. You see, when you multiply out these things, you get a sum of sigma I, sigma j, and then you have minus I di minus AI, minus, I'm too fast here, minus I dj minus aj, right? So this is your operator. And now you notice something interesting, namely the sigma i's, the Pauli matrices, when you square them, you get the identity, the 2x2 identity matrix. And when you look at sigma I, sigma j, then you notice the anti-commute. So you see, what happens now is that when I is equals j, you sum it, you get the first term. When I is not equals j, you look for this antisymmetry, and what you notice is that the derivatives term go out, the ai with the ai goes out. What you get, however, is the derivative terms combining with the a's. And this produces precisely the curl of A, which results in sigma times B, okay? By the way, an interesting formula in this business is always the following. When you take any two vectors A and B, that turns out to be A dot B times the identity plus I times sigma dot A cross product B, okay? These are somehow these identities which you have to jiggle in this business, okay? So in other words, when I go back to this functional here.
Michael, there's a question.
Yes,
this
please.
might be a silly question, but when you find your E of B and Z before you added the magnetic energy,
Yeah.
you said this can be, we can cook it up to be as small as possible. Do we even know, is there an example where this infimum doesn't exist when it's minus infinity? Do we have any detail that it's not constantly minus infinity?
You mean you're talking about this functional here?
The sorry, it's hard for me to see. The one that you have squared, the infimum.
Oh, this one here. Yeah.
Why is this?
Yeah. Okay. Yeah. So whenever you take a magnetic field with finite field energy in general, yeah, a fixed one, then the infimum exists.
Okay.
They have a minimizer. Yeah. Okay, and it's finite.
Yeah.
Yeah. But of course, now when you start varying over the magnetic field, things are a little bit unclear. You agree?
Yeah.
Yeah. So you can push the electronic energy down towards minus infinity, right? But of course, you pay then the price maybe in the field energy. Do the balance? That's the question. Okay.
Yeah.
So yeah. So now you see with this identity here, you can actually look at this problem in the following sense. You introduce. Let me do this on the next page. 6. I introduced the functional E of psi and A, which is equals to sigma dot minus I grad minus A psi squared. Let's make sure that I write this nicely here. By the way, can you read my handwriting?
Yes.
Yeah.
Okay, good. And then you get, of course, minus the z times the integral of psi squared divided by x. And then you add 1 over 8 pi alpha squared, the field energy. And what you then do is you look for the infimum of E of psi A. And what you do, taking the infimum on over all psi's which are normalized. I'm going to write this as psi 2 equals 1, and I'll be with finite field energy, right? And you ask the question, well, what is that? Yeah. Now, this was a problem which we considered, my goodness, I mean, again, almost 40 years ago with Jörg Fröhlich, Elliot Lieb, and myself. What's the answer? Well, I would call it the destruction of the uncertainty principle. You see, the kinetic energy, you stashed all in here, right? Well, kinetic energy has also the B dot sigma term in it. And this term has a possibility to cancel. Okay, so now let's imagine for a moment that we have a solution of the following equation. Sigma dot minus I grad minus A psi equals 0. Suppose we have a solution. So this is a terrible equation, right? It's actually a system. Let me write it out so that you see it in front of you. This is what? This is sigma 1 minus I d1 minus a1 plus sigma 2 minus I d2 minus a2. Of course, that you can all imagine. A3. And if you think of a matrix, it's a matrix equation. You get minus I d3 minus a3. And then you get plus I d3 plus a3. And here you have minus I d1 minus d2. This and minus I d1 plus d2. Right? And then what you have to do is you have to apply to a spinor psi 1, psi 2, and you have to solve this for 0, right? But you see, it's not only that. The spinor should be normalizable, and the magnetic field and the A potential should belong to a magnetic field which has a finite field energy. Suppose, for the moment, you have something like that, okay? You see, such an equation doesn't impose a scale. What you can do is you can introduce A lambda of x, which is lambda A of lambda x. And you introduce psi lambda of x, which is lambda 3/2 psi of lambda x. Lambda is any positive, if you like, real number. And what you notice is that the psi lambda, I mean, this lambda 3/2 you put here, that the normalization is preserved. It's a standard trick, right? And what you now notice is this lambda here has the added bonus that sigma dot minus I gradient minus A lambda psi lambda is still 0, right? You see the derivative pulls out a lambda from the psi, and the A has already a lambda in, the lambda comes out. So in other words, you can rescale the A and the psi in this fashion, and you still got the solution of the 0 mode. Okay, good. And then what you do is you take your functional psi A, and you stick in psi lambda A lambda. What do you get? Well, this term is equal to 0, right? This is precisely how we cooked it up. And then what you have is you have the rescaled psi in here, and you have the rescaled A, which is actually the curl of it, in there. And when you work out what this rescaling does, you learn that this is just lambda times minus z, the integral psi squared over x, plus 1 over 8 pi alpha squared, integral b squared. Okay, so in other words, what happens to you now is if you choose the z for some strange reason large enough, so suppose this parenthesis is negative. So you choose the z large enough so that this is negative, then you let the lambda go to to plus infinity, and you can drive the energy to minus infinity. Also put it differently, if the z is large enough, I think that's the answer now to Amit's question, right? It was Amit who said it, right?
Yeah.
The infimum is minus infinity. If you have such a zero mode, right? And if the z is large enough. And now, of course, if one talks to physicists, there is a moment of silence, and then, of course, you say, well, this cannot really be physical, and indeed, it's not physical. With a lot of work, you can somehow figure out that when the z is less than 20,000, okay, you have this phenomenon cannot happen, right? So, atom is stable. So I mean, in other words, this problem really doesn't come up in any kind of real world, except maybe in neutron stars. But then you would have to have a relativistic theory, because when you make a sort of a ballpark estimate on the size of such magnetic fields, they have to be somewhere around 10 to the 18 Gauss, which is not something you see on the Earth, but you see it in neutron stars. At least one believes that, right? Okay. So this was just, if you like, an introduction. This problem was actually dealt with by as I said, by Fröhlich, Lieb, and myself in 1986. We wrote a few papers about that. So now, of course, they still haven't really answered the question, is there such a zero mode, right? And the answer is yes. Are there zero modes? Yes, there are zero modes. And this is something which I worked out with Hong-Tzu Yao, which is a famous mathematician now, right? This was his first paper, actually, we wrote together. I just write down an example. Psi, I indicate this by H, you will see the reason later. Phi is any constant normalized spinor. And what is the A? The A turns out to be 3, 1 plus x squared. And then you have 1 minus x squared w plus 2w dot x plus 2w cross. And this is the cross product. Now, since I use x, then wxx wouldn't be good, so I put a wedge. I hope you don't mind. Of course, the w is now a constant vector, normalized. Sorry, there is something going on with this thing. And what you need a connection between the spinor and A, I call it AH. And what you need is that omega or W is phi, this constant spinor sigma phi. And then you learn that sigma minus I grad minus AH, psi H is equals to 0. And what you notice, of course, is that the AH is a very nice field, right? It decays like 1 over x squared. When you take the curl, you get a magnetic field. By the way, interesting. The magnetic field decays like 1 over x to the fourth. It's beautiful, and it's proportional to A. These are these examples which are called chaotic fields, where the curl is proportional to A. So you cannot integrate that field, right? You cannot write it as by multiplying by a function to write it as a gradient. These are somehow complicated fields. And yeah, by the way, another interesting thing about this is sigma minus I grad. When you look at this psi, this actually satisfies this equation. And you see, once you realize this, it's very easy actually to cook up this magnetic field or this vector potential. And the way you do it is this, that you remember that when you take psi, sigma psi, now you have it, right? You divide by psi psi, and you multiply by that this is equals psi. So therefore you get right away that this guy here, applied to psi, is 3 over 1 plus x squared times, let me write it differently, sigma dot 3 over 1 plus x squared psi sigma psi. And this, of course, is now your A potential, right? This turns out, this was the trick actually in order to figure out what the solutions were. We knew that this was a solution, and then it was very easy to cook up this vector potential, okay? So this is the situation. So we have now these zero modes. They exist. They are in some sense real. But there is some strange beauty about those. And let me explain this a little bit. I mean, one thing which we didn't know really what this, we didn't know what this was. And the next question is, well, how do these field lines look like, right? And fortunately, I ran into Oliver Penrose at that time, and he explained to me that this has something to do with twistors, or rather the Hopf vibration. And let me now sort of show you how these field lines look like. Namely, what is the Hopf vibration? The Hopf vibration is, this was discovered in the 1930s, I think, by Hopf. This is an interesting thing. If you take the S3, of course I cannot draw it, right? So here I give you a picture of I write it as S2, but it's actually S3. Now you see the S3 is really the sphere of all normalized spinors, right? Each spinor has two components, complex numbers. So in total you have 4 real numbers, and the sum of the squares of these real numbers is 1. That's the sphere, S3. And now you take this map, psi, sigma, psi, and I told you that the norm, the length of this map, psi, sigma, psi, is 1, is psi, comma, psi. So in other words, you have a map from the S3 into the S2. When you take a point on the S2 and you look at the pre-image, you get great circles in S3. And these great circles have a strange property, namely they're one-dimensional, of course, and what they interlink. And you see these great circles, you can immediately understand them, because if you multiply the psi by a phase, nothing changes, right? Psi, sigma, psi stays the same. But of course, in S3, you produce a great circle. And of course, you can take different spins. I mean, here's a point P, here's a point Q on this sphere. The P corresponds to a psi, the Q corresponds to a phi, and you create these circles. Now, of course, it's really, really hard to imagine how these things look like. And there is a trick, which I think Eric...
Michael, there's another question from the audience.
Yeah,
yes, please.
I mean, perhaps like just a reminder. So I guess like what you mean by psi, sigma, psi is the map going from S3 to S2, is that where you get...
That's right.
Each of the Pauli like matrices, then you get a vector of 3 coordinates.
That's exactly right. Yeah, yeah, right. So the psi sigma psi, you have a psi sigma 1 psi. That's, remember, was 2 times the real part of psi 1 complex conjugate psi 2. The other one was twice imaginary, and the last one was the sigma 3. So you have 3 components, right? And when you look at the length of that vector, you get the vector on the S2, right? Exactly. So So this is how it looks. I mean, it's a little bit hard to visualize how this circle should look like. And there is a nice picture. Let me show you one. You use the stereographic projection, right? Maybe you remember that what you do, you take the sphere and you take a plane, and the plane, if you like, is attached, it cuts the sphere in the equator. And then you pick a point on the sphere and you connect it to the South Pole and you intersect this plane. You get a point. So this map from the sphere to the plane is called the stereographic projection. And this has nothing to do with dimensions. You can do this in any dimensions. So you get a map from SD to RD. So that's standard. I think the first one who actually wrote it down in one dimension was Diophantus. But anyhow, it's at the moment not so important what this is. But once you pull back this Hopf, what shall I say, the Hopf vibration, that's what it's called. When you pull it back with stereographic projections to R3, you get sort of a better picture. And here's a nice one which I discovered by Anatoly Katok. You have to sort of imagine that the field lines, they sit on tori. And the field lines are really Euclidean circles. So you have one circle, it's like a donut which you cut by these circles. And you see what the circles do, they interlink. And then you have this whole nested sequence of tori, okay? These are the field lines of this Hopf vibration. And here maybe you have another little picture which you found from a picture from the CNRS. You see you have this line here, this red line, and around it you see this nested tori. Now, what is a little bit misleading is it seems that there is a certain direction which is important here. On the sphere, of course, you don't have a special direction. This has to do because you chose a certain direction for the stereographic projection. When you choose the South Pole, this axis is north. You can choose, of course, any other point for the stereographic projection, so you get different axes, right? So this is the Hopf vibration. And what turns out, that's in some sense the beauty, is that this A potential, which I've written here, has precisely these patterns as field lines. Okay? So that, of course, brings up a bunch of questions. I mean, is there something special about that, right? So we ask ourselves now the following question. Find optimal necessary conditions for on B, I should say, on B, and A, if you like, for zero modes. How to formulate those? Is the Hopf pattern, in other words, psi H and AH distinguished? Do they optimize something, right? Okay. Do they play a special role? Special role in binding electrons. Okay, so this is the question which sort of comes up in a natural way here, right? I should also say that this zero mode equation, so this equation here, sigma minus IA grad minus A psi equals 0, you see, we are in R3. And that's a terrible dimension. Odd dimensions are somehow terrible for this problem. When you're in 2 dimension, there is this device by Aharonov and Kasher. They classified completely all the zero modes. And that's a very stable thing, namely, it's just the flux of the magnetic field through the plane, which determines even the number of zero modes. So in some sense, you have an index theorem. There's a topological reason why these zero modes exist. Here in 3 dimension, no topological reason is known. For example, if you have a zero mode and you change the constant in front of the A a little bit, it disappears most of the time. It's a very unstable situation, right? So things here are not in some sense purely topological. You need in some sense analysis and other tools in order to analyze this, okay? So this is the setting. And now what I would like to do is I would like to start studying this equation in seriously, right? So what are, if you're interested in figuring out what are good conditions on B and A, what you have to find is, of course, conditions which are scale invariant, right? Because you know, when you scale the A, you still have zero modes. So these quantities better be scale invariant. And one quantity which is scale invariant is, of course, the integral B of x to the 3/2 dx. And of course, also the integral of ax cubed dx, right? Because when you scale A, plug it in, you see right away that this is scale invariant. What is the curl of A? Lambda. So this is A lambda. Curl of A lambda, which is B lambda, is of course lambda squared B of lambda x. When you plug it in, you see this is also scale invariant. So it is natural for us to assume that the 3 norm of A is finite. So we will study now this equation with A's whose 3 norm is finite. Okay. Oh, until when do I have time? I have 90 minutes, right?
90 minutes, so another half hour.
Okay, good.
In fact, we started.
So maybe, sorry?
In fact, we started a few minutes late, so we should take some time for questions.
Okay.
35 minutes.
Yeah, okay, good. So now, let me first study these equations a little bit. So the first question, of course, you have is, for which psi's can you expect such solutions? And what we're going to look at, we're going to look at psi's which are in LP of R3 with values in C2, of course, for some P bigger than 3/2. This is natural. Now, why do we have P bigger than 3/2? Because you see, you need that the A times psi is at least locally integrable, right? So that you can talk about a weak solution of this equation. That's natural. Agreed? So when the P, for example, is less than 3/2, then of course all bets are off. You don't know anyhow how to think about this term, right? It doesn't even make sense as a distribution in general. Okay. So here is a little theorem, which I think is not without interest, and also the proof is not without interest theorem. It's a regularity result. Fix some 3/2 less than P less than infinity, and let psi, let me write this a little bit better, psi be in LP of R3 values in C2. From now on, I will drop this. I mean, it's clear what we're talking about. Be a solution, a weak solution, right, of sigma dot minus I grad minus A psi equals 0. A is not given. The 3 norm is finite.
Michael,
Then,
are we no longer assuming psi is normalized in L2 because that's bigger than 3/2?
Yeah, no. For the moment, that will come, right? let me write down the theorem. Then psi is in LR of R3 C2 all R bigger than 3/2 less than infinity. Okay? So in particular, it's automatically in L2. Does this answer your question?
Yeah. Mm-hmm.
Right? So this is kind of neat. In particular, you see, why is this a good thing? It also tells you that the psi is in L6, right? And in particular, A psi by Holder's inequality, so consequence, A psi is in L2 by Holder's inequality, right? A psi 2 is less than A3 psi 6. And therefore, because of the equation, you realize that sigma dot I, minus I sigma dot grad psi is in L2. Okay? Not only is minus I sigma grad psi in L2, but now you notice the following by Fourier transform. If you think about this in Fourier space, this is nothing but sigma dot k squared psi hat squared. But sigma dot k squared, you can easily check it out what it is. It's sigma dot k squared is k squared, k dot k, plus I times sigma k wedge k, which of course is 0. So you learn that this thing is nothing but the integral of modulus of k squared. I think I forgot a bunch of 2 pi's here. Depends how you define the Fourier transform. Or, okay? So you learn right away that the psi is in H1. Okay? So this is this theorem, which will be very useful in what follows. And I think the proof has some interest. Yeah. So let's try to prove it. So again, let me say what it says. If you fix any psi in LP, where some p is some number between 3/2 and infinity, then the psi is in any LR when R is between 3/2 and infinity. Okay. That it actually is L infinity, I don't know. In general, it's not true, I think. But I don't know at the moment a counterexample offhand. Okay. So this is regularity result, if you like. So let's try to prove that. So proof of the theorem. So this all will boil down to uses of the Hardy-Littlewood-Sobolev inequality. Let me write this down, what this is. If you take x minus 2 and you convolve it with some function f, and you take the q norm, that's always less or equals a constant, which in principle you can compute, times the f p norm. But you need a relation between q and p. And remember, we are always in R3. So you learn that 1/3 plus 1/q is equals 1/p. And 1 must be strictly less than p, strictly less than 3. This is the Hardy-Littlewood-Sobolev inequality. Well known. Okay. I will abbreviate this HLS. So, great. So the first observation is when you, yeah?
3, did you mean 2? P less than 3?
Hmm? So this is a 3 here.
Good.
Are you
Good.
are you okay?
Yeah.
Yeah. I think the dimensions work out, right? I mean, that's true, right? Okay. Yeah, that's right. Good. So this is what we're going to use all the time, right? So remember that. So you take a function, you convolve it with 1 over modulus of x squared. That turns out to be a function in LQ, provided f is in LP and Q and P satisfy this relation, right? That's what the story is. And P must be a function, an index between 1 and 3. So you notice that the peak, for example, cannot be equals to 1. And the peak can also not be equals to 3. That's impossible. P equals 3 would mean Q equals infinity. X minus 2 star F is never infinity in L infinity. I mean, most of the time, should say. Okay. All right. So now the first step which you do in this proof is the following. We're going to write this equation minus I sigma dot grad psi equals sigma dot A psi. And what we do is we invert it. How do you invert this? You introduce gamma of x. That's I sigma dot x 4 pi x cubed. And you notice now I claim, huh? or let me write it differently. Introduce psi twiddle of x, which is gamma convolved with sigma A psi. So claim psi twiddle is equals psi. And that's basically quite straightforward. You notice, by the way, that psi twiddle P norm is less than a constant times psi P. That's already clear. You agree? Because you see, the psi is in LP. The sigma A psi is in LQ because this is precisely this relation of Hölder's inequality, right? And then what does the gamma do? Well, that's the convolution. Am I saying this right? Let me think for a second. I think that's HLS, right? So let's check. Yeah, no, that's right. HLS does that, right? Because if you take the psi in LP, and then you take sigma A psi, and then you see that this actually is in, yeah. So you have to change the P and the Q, right? So what is it? Psi twiddle P norm is less than what? Well, that's equals to this sigma dot A psi in R norm, right? We use Hardy-Littlewood's overlap. So the Q I have to replace by P. So I have 1/3 plus 1 over P is equals 1 over R. And then that guy I estimate by A3 times psi of S. And what is A3? That's 1 over R equals 1 over 3 plus 1 over S. You agree? That's Hölder. And you see right away that the S wants to be P, right? So that works out. Okay? I was just at the moment a little bit confused about this. So let me erase this now because that's pretty clear. So I claim that the psi twiddle, oh, it doesn't want to go. Huh? All right. The psi twiddle is equals to psi. We have to prove this, and this is not very difficult. You notice, by the way, that sigma minus I grad, when you take the difference, is equals to 0. In other words, the spinor psi twiddle minus psi turns out to be, right? I mean, because when you put sigma minus I grad on psi twiddle, that kills this guy. because that's the Green's function. You get sigma A psi, and the psi, of course, also satisfies the equation, so that's 0. And then you notice that this is a harmonic spinor. And when you compute minus in the distribution sense, which always works, you just apply sigma minus I grad once more, and you get the Laplacian. So this is harmonic. Now, and therefore, C infinity, in fact, real analytic. The difference is real analytic. And now you notice that B, when you fix any point A, and you take a ball of radius R, and you look at this difference, that's less than, by Hölder's inequality, the volume of the ball to the power 1 over P prime times psi P. Okay? And you see, therefore, when you divide by the volume of the ball, this you have is a negative power. And when you let R go off to infinity, you get 0, right? So therefore, psi equals psi twiddle by the mean value property, yeah? Right? Because when you have 1 over BR, psi averaged over BR of A minus psi twiddle, that's psi minus psi twiddle of A. That's because it's harmonic functions. Okay, so we now know that we have now an honest description of psi in terms of this equation. Next, we're going to analyze this. So what we're going to do now is fix any R between 3/2. And now we have to distinguish a little bit. It's 3P over 3 minus P when P is between 3/2 and 3. By the way, this simply says that 1 over P minus 1/3 less or equals 1 over R. Actually, you can have a less or equals here, less than 2/3, right? And when P is bigger than 3, we simply can choose any R bigger than 3/2, less than infinity, right? So let's fix this, right? So if your P is between these two numbers, you fix the R to be any number here, whatever you like. And here, if the P is bigger than 3, I fix the number, any number between these two. All right? And what we're going to show is, we shall show that psi R is less than the constant psi P. By the way, this proof which I'm going to give had sort of a little history. We got this, I mean, with Rupert Frank together. I forgot his name again. They already, I mean, it's not new what I'm telling you. This has been known for some time. But it's kind of a nice idea. So now fix any M. So here's the trick. Positive number. And look at the following gadget. So remember the psi is given, right? And the gadget here is that you take any phi with R prime less or equals 1. Now you see, when you take this supremum only with this condition, what would you get? You get, of course, precisely the R norm of psi. But that, of course, is precisely what we'd like to prove, that this is finite. So now you impose the condition that phi P prime is less or equals M. This is this number S, M. Okay? So then what we do is we go and we look at sigma dot A and we split it. So this is a Hermitian matrix, and we can split it into two matrices, functions, right? F epsilon is bounded, compact support, and the G epsilon has 3 norm G epsilon. That's tricky. An epsilon and a 3 together, that's always a problem. Okay? So this is what we want to do, right? Good. So then you can say, how does the psi look like? The psi is then given gamma F epsilon psi all right. And what we do now is we pick any phi in LR prime intersect LP prime. Remember this SM, let me put this in the red box because that's in some sense is the key idea. And then we consider the integral of phi psi equals the integral of phi gamma star F epsilon psi plus the integral of phi gamma star G epsilon phi. Okay? So now let's concentrate on the first term. The second, I will talk about this, the term afterwards. Well, this term, so let's just call it 1. Let's call this one 2. Term 1 is in magnitude less or equals. Well, you just use Holder. Because now we use some nice properties of the F epsilon, and this is R less or equals phi R prime. Remember, phi R prime is in SM would be less than 1, but let's keep it this way. Times F epsilon psi S. This follows with Hardy-Littlewood's Sobolev. Right? 1 over S is equals 1 over R plus 1 over 3. And that you can in turn estimate by phi R prime SP over S minus P by Hölder. And where I interpret the SP over S minus P to be infinity when S is equals P. Now, the S, you notice, is now any number between 1 and P. And it's given by 1 over S. I said it here. You can easily check that this condition with this R turns out that this is correct. This always is the case. Okay? So now you see the F epsilon is always nice, right? It's bounded, has compact support. Yeah. So this is finite, even in L infinity. It has all the nicest properties, all the properties your heart desires, right? Good. All right, so let's concentrate on term number 2. I have another 10 minutes. Term number 2, magnitude. Now this term I'm going to write as G epsilon gamma star phi psi. So what have I done? I moved the gamma over. You're just taking the adjoint. It's self-adjoint, in fact. You can push it over. And then I have the G epsilon on this side. And the next thing which we're going to show now is that this function, let's call it high epsilon is in LP prime. Okay, let's prove this. It's again easy. Chi epsilon P prime is less or equals G epsilon 3, you get the gamma star phi. And what is it, T, which of course is less than the G epsilon, which you keep, right? 3 phi P prime. This is with HLS. And by the way, I drop constants. I mean, these are universal constants. Whenever I drop the constant, it's a universal constant, which has absolutely nothing to do with epsilon or phi or psi or whatever, right? And that, of course, is less than a constant, if you like. Now keep it times m. The phi, remember, this is what we need. The next fact is that the chi epsilon r prime is exactly in the same fashion, using Hardy, Littlewood, Sobolev, and Hölder. It's all really elementary. S, I write it this way, is less or equals a constant times G epsilon 3. And then you have the phi r prime again, right? Where 1 over r prime is equals 1/3 plus 1 over s. And that, of course, is less or equals C times G3, G epsilon 3, if I think that this phi of r prime is in this set. Very good. And now, so you see, the phi of r prime, the chi epsilon of r prime is not normalized, right? It's not strictly speaking in this set Sm. Likewise, its p prime norm is not really strictly speaking bounded by m. There's a constant in between. But now what you do is you notice that phi twiddle equals chi epsilon divided by a constant times G epsilon 3 norm. Satisfies? Phi twiddle r prime less or equals 1, and phi twiddle p prime less or equals m, right? This follows from these two estimates. So overall, what do we have then? We have then the integral of phi twiddle psi, right? I just have divided here by this constant times the G3, is therefore less or equals Sm. Or, if you like, the integral of chi epsilon psi is less or equals constant G epsilon 3 Sm. And I think I might manage to do this. Okay, so these are this very elementary, all is Hardy, Littlewood, Sobolev, and Hölder, nothing else, right? So you have this estimate here. We also had this estimate before term 1. So when you collect the two, this estimate here, together with this estimate in the box, what do we learn? We learned that the integral of phi psi magnitude is less than a constant, let's call it C2 if you like, f epsilon ps over p minus s, psi p, plus sm c1 g3 g epsilon 3. Okay, very good. So now remember, the G by assumption, I still have this parameter epsilon, which is free. We had this assumption that this is less than epsilon, less or equals. So we learn that the Sm, remember, this is, I take the soup now over all these phi's, I learned that the Sm is less or equals what? Well, C2 plus Sm C1 times epsilon. And therefore, if we choose the epsilon, for example, equals 1 over 2C1, this is a universal constant, right? We learn that the Sm is less or equals twice C2 F epsilon Ps P minus S psi P. Okay? And you notice the right-hand side doesn't depend on M. The F epsilon is now fixed, right? The epsilon is chosen. The F epsilon is fixed. This is maybe, 2C2. This is maybe a humongous constant. I don't care. It's finite. And therefore, the Sm is independently of M bounded by psi P. So we take the soup, and what we learn? We learn that the psi R, remember the definition? Where was it? Here. Right? This M now doesn't play a role. I can actually let it go off to infinity. And what do I learn? I learned that the Sm gives me an estimate of the type that psi R is less or equals some constant psi P. And therefore, psi is in LR. And that proves it. Okay? So I find this is sort of a not very difficult. It's kind of an attractive thing. And I think I have written out somewhere the names of the people who discovered this. Let me check. Where were they? Yeah, I have my notes here. And I think I forgot it. Yeah, I cannot find it for the moment. Maybe next time. Okay. So anyhow, I think maybe it's a good idea to stop here. So what I'm going to do next, you see, so that settles in some sense the technical issue about this zero mode equation, right? So you take any A, which is in 3 norm is finite. Suppose you have a solution in some LP, P bigger than 3/2. It's in LP, in LR for any R bigger than 3/2 and finite. Okay? So next time, we're going to now get more into the sharp inequalities and show a few ideas. And this is going to be a mix of some analysis, some algebra, and some differential geometry, right? And let's see how we get there. So I think I'll stop here, and thank you very much for your attention.
Okay, thank you. Okay, so now we'll have some time for some questions. I'll actually, as moderator, take the advantage. Could we go back to page 1, to the very beginning?
Very beginning. Oh my goodness, I have written a lot of.
You've written lots, right?
All right.
Okay, the hydrogenic atom.
Yeah.
Okay, and you were mentioning that you get the lower bound with the right radius of the atom by using the Heisenberg uncertainty principle to control this, but I'm familiar with doing that.
No, by this. I meant by actually solving it, right? Yeah.
Okay. Right. Well, okay, there's the uncertainty.
Yeah. I mean, Heisenberg doesn't give it to you.
Doesn't give it, right? That's what I thought. But then with Sobolev inequality, then you do get the right thing.
Oh yeah, absolutely. No, Sobolev doesn't give you the right constant. This gives actually c squared over 3.
Right, but the right order of magnitude, but not the sharp value, but the right order of magnitude.
Right, exactly.
But not Heisenberg.
But you see, I mean, you no Heisenberg not, right? I mean, what is the counterexample? Half of the wave function is near the atom, and the other half is behind the moon, right?
Right.
Yeah, that's a disaster. No, Heisenberg is useless in this kind of business.
Okay.
I mean, not Heisenberg himself. The Heisenberg uncertainty principle.
Uncertainty principle doesn't give you that. Right. Okay. And now in the scalar case, then of course you immediately know the psi is in H1, and then Sobolev says you're in L6 and so forth. But so the second part of the story here, then we have to argue more. You have to argue more carefully in this Spinor case because there could be cancellation between the A and the gradient. So the finite
Exactly.
energy doesn't tell you you're in H1 for free, but in the end you are because of what you just
Yes, right. Yeah, exactly. That's right. It doesn't tell you, right? I mean, it's tricky. Yeah.
So is there an inequality with this kinetic energy involving the vector potential, an inequality that says that that thing controls the H1 norm of psi?
Yeah. Well, in fact, I will show next time that when you have a zero mode, you have actually an improved diamagnetic inequality.
Mm-hmm.
Okay, so these things go all back. I mean, it has a long history in a way. When you look into the literature, many people talk also about the Kado-Yau diamagnetic inequality, and we will, and then there were some people like Herzlich and other people, mostly people from differential geometry. I think these ideas were also important for this Calabi-Yau conjecture in the proof. So there will be a diamagnetic inequality, so which will tell you that the magnitude of the spinor is bounded by, in some sense, the kinetic energy, but with a better factor than 1.
Okay, very good.
Is that what you meant?
Yes, right. Okay. So the other questions from the audience. Hey, Amit.
You're actually the right slide, Michael. I'm sorry, I can't see very well the power, but the example you've chosen, the psi h, part of it looks like the optimizer of the Hardy-Littlewood-Sobolev inequality.
Yeah.
A lot. Is there any...
Yeah, right. Exactly. Absolutely right. So let me just say, I mean, so you have the sigma term here, right?
Yeah.
Yeah. So take the magnitude of the spinor. What do you get? You get 1 over 1 plus x squared. You agree? Because the magnitude of 1 plus I sigma x, when you take the magnitude, you get 1 plus x squared to the power 1/2. That cancels 1 power of from the 3/2 down to 1.
Yeah.
And that is not quite the Sobolev optimizer, but its square root is.
Yes.
And for some reason, we can use that to get good results.
So is this more
you will
luck
see that.
than anything else? Because it just seems so nice that you get something so close.
Yeah, that's right. But you see, the problem is, yes, it's so close and at the same time so far, right? Because you're talking about what? 4 complex functions, which you have to somehow squeeze together in order to get a sharp inequality, right?
Yeah.
Yeah, no, you're right. Yeah.
But I guess the related is this factor of 1 over 1 plus x squared to some power, is that arising as the Jacobian of a conformal stereographic projection?
Yes, that's right. Yeah, that's right. Exactly. Yeah, because this 3-dimensional Dirac equation is actually conformal invariant. You can look it on the sphere, and this is what, by the way, Jan-Philipp Solovey and Laci Erdős did. They actually classified solutions of this type. These are not all the solutions, right? There are more, and many more which are not of that type. But they actually classified those solutions which arise through the Hopf map. That's what they did. Yeah.
Okay. Further questions? So that seems to be all the questions for today. Okay. So thank you very much, Michael.
And then we see each other on Thursday, right?
See you on Thursday.
Yeah. Okay. Good. And then I sort of chime in a little bit. I'm listening to the talks. I hope I can still listen to some of the talks, Patricia.
Yes. Patricia is not here, but of course we will manage in such a way that you can follow. Of course, Michael. Thank you.
Okay. Great. Yeah. I mean, if it's really hard, then don't bother. But
No.
Okay.
Now we
good.
have a coffee break, and we will come back in 30 minutes, more or less.
Okay. Okay. Good.
See you later.
Thank you. Thank you very much.
Thank you.
Bye-bye.
Optimizer.